All right, this is a video for Thursday in geometry, and we are going to finish up the day 1 and 2 packet. But before we do that, I wanted to make sure that you understood the difference between central angles and their arcs and inscribed angles and their arcs. And then a lesson maybe Friday or next Monday, Tuesday, sometime in there, we will get more into this very simple topic. In the video for Wednesday, I think it was, I showed my anchor charts on these. But if you'll notice on these two circles, all right, I have a central angle right here because it's at the center point. All right, this angle is at the center. And I have this listed as 35 degrees. So the question then is, well, then what would this arc measure be? Okay, right there. Well, that arc is going to be the exact same, okay, as the central angle. So that arc measure is going to be 35 degrees, okay? So the central angle and the arc that it goes to are always going to be the same degree measure. Okay, so on this example, we've got this arc that I've outlined here in purple as 200 degrees. So it's a major arc, all right? It's more than just a half of a circle, more than a semicircle. It's a major arc, all right? So to find x, the central angle, it's going to be the same as that arc. So that's x for that is going to be 200 degrees. Okay, 200 is what
Siri here.
Angle X will be, okay? Well, if that's 200, then in the whole circle, that's comprised of 360 degrees, so we can easily find angle Y. Angle Y is going to be the supplement, I shouldn't say supplement, is going to be the angle that then adds up with x to make 360. So if x is 200, y has to be 160. Okay? 160 degrees. And the reason, because those two angles are both central angles, and they then will make up the whole circle there, since those are the only two angles in the whole circle. So x is 200 degrees. All right. Y is 160. Well, what's Z? Z is then the arc that goes from this point here to this point. Okay. So what would that arc measure be? It's going to be the same as that angle measure. So Z is going to be also 160 degrees. Okay. So that's real quickly helping you understand the basics of central angles and the arcs that they go to. The other types of angles that we had in yesterday's notes on the parts of a circle are what are called inscribed angles. Inscribed angles are angles that the vertex is on the edge of the circle. Okay? So if this arc here is 50 degrees, all right? If that's 50, all right? What that means is that arc is the measure of from the central point that I'm just kind of, let me get a different color pen so you can see this. That angle that goes to that arc is a 50-degree angle then, okay? So if this arc's 50, that central angle that would go to that arc is 50. But what's this angle? See, this angle is not as wide as this one. So how do we figure that out? Well, it's very simple. My anchor chart yesterday says that an inscribed angle is half of the arc that it goes to. So if this arc is a 50-degree arc measure, then angle X is half of that. X would be take that arc and divide by 2, right? So that means angle X is a 25-degree angle. Okay, and you can see my work on that there. And then the one over here on the right, if this is an 80-degree inscribed angle, why? Because the vertex is on the edge of the circle, okay? And once again, if that's half of this arc that it goes to, this arc here is 80 degrees. I'm sorry, this arc here is what we're looking for. Okay, so I take the angle 80, right? That is half of the arc that it goes to. Okay? So the angle is equal to the arc measure, which I don't know, divided by 2. That's how I would set that up to ultimately solve. And then in finalizing that to solve for x, I would multiply both sides by 2. And so 2 times 80 means that that angle measure is 100, or that arc measure is 160 degrees. So see, the arc is double of the inscribed angle. The inscribed angle is half of the arc that it goes to. 80 inscribed angle is half of the arc. The arc is twice as long as the inscribed angle. Okay? 50 degrees was this arc. What was that angle? 25 degrees. Okay? So I just wanted to kind of show you that. All right, let's get to finishing up our notes from yesterday. So if you take this packet, all right, Unit 4, Task 1, Day 1 and 2, we worked through all of the different definitions and the parts, and we got to this page here. I'm going to enlarge it so we can see this again. I got to this, what, third page, I think it is, and we started to learn about tangents. And so down here, we've got tangent lines. A tangent is a line that is on the outside, it's on the exterior of the circle, and it touches a circle in one spot. It doesn't go inside the circle on the interior, okay? So as you can see, this line is tangent to this and tangent to this circle. It's touching this big circle right here. It's touching this smaller circle right here. So these are called exterior tangents to these two circles. The red ones on this middle, exterior tangents. But interior here, in between the two circles, I can also draw these two lines, and those are interior tangents, okay? Or internal tangents. All right, and then on the very right-hand side, you can see that this circle inside of this other circle, this tangent is coming and touching both circles at one spot. And that would be an exterior tangent, or external tangent, I guess I should say. And then down at the bottom of this page, you can see we've got another example where two circles are touching each other just on the edge. And so I drew the external tangents in red, and then this internal tangent in blue going straight down, and right basically here is where those two circles and that tangent are all touching each other, like right there. Okay, so I wanted to refresh you on that, and then this is the new stuff for today. Okay, new for today is right here. All right, so a radius, we're looking at properties of tangents. A radius drawn to the point of tangency. So as you can see here, I've got a radius that is drawn here and then here. And where I have this tangent line, all right, here's what's kind of cool about this. Why must the radius always be the shortest distance from the center of the circle to the tangent? it's always going to be the shortest distance. And the reason why is because wherever you have a radius touching a tangent line, that's going to always be a perpendicular spot. All right, so even down here, this radius and this tangent line, when they intersect or touch each other right there, that's perpendicular. And so always, you probably learned a long time ago as a kid, the shortest distance between 2 points is to walk straight perpendicular to that point. So, like if you're in your backyard and you need to walk to, maybe you have a fence, wherever you're at, you need to, the shortest distance from where you're standing to the fence is to walk perpendicular to that fence. Okay? And so, always, when you have a tangent line, the radius that will go to that point of tangency is always going to be the perpendicular angle, and that will always be the shortest distance from the center to the tangent line is always going to be the radius. Okay, so what kind of line is the shortest distance from a point to a line? A perpendicular. All right, a perpendicular. All right, so let's continue on. Consequently, a radius drawn to the point of tangency is the perpendicular to the tangent. Okay, so if they didn't give you that it was perpendicular, you can draw that perpendicular box in there. Why can we do that? Because we have a radius here, and AB apparently is a tangent line. It says, how can you test to see if AB is the tangent to the circle? So we're going to see if that is tangent or not. Now, notice the measurements that they give us. I'm going to enlarge it a little bit more on this so we can really see this. Notice the measurements. This radius length is 3 long. Side AB, so from B to A, is 4 long. The only other measurement that they gave us was this measurement right here. From B to the edge of the circle is 2. Well, where did I come up with this 3? I came up with that 3 because it's another radius. I'm going to draw it right here in purple. All right? This right here is a radius. And if that radius is 3, radiuses in the same circle are always going to have the same length. So that's 3, which then makes this whole side from the center of the circle to be 5 long. So we have a right triangle. 3 is the short side, the medium length side is 4, and the hypotenuse is 5 long. So how can we always test to see if we have a tangent line? We can do what this is doing and make a right triangle and use those different measurements to see if it makes a true statement. So 3 squared plus the medium length side, 4 squared equals the hypotenuse squared. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. Sure enough, 25 equals 25. That works. So I know that on this one, sure enough, AB is a tangent. Okay, so a big whopping yes. All right, let's go to the next one. Over here. Same basic setup. I have a radius that is 6 long. I have what looks like is a tangent line of 7 long. And I have this little measurement right here from the edge of the circle to B as 5, it looks like. And this radius is the same as that radius, so it's 6. So that means this whole length here is 11 long. If this is a right triangle, I will have 6 squared plus 7 squared equals the whole length of that triangle is 11 long, right? So 6 squared plus 7 squared equals 11 squared, Pythagorean theorem. And so that's how you can test. You use the Pythagorean theorem to see if it makes a true statement. 6 squared is 36, 7 squared is 49. 36 plus 49 is not equal to what the hypotenuse is 11, So when you square 11, you get 121. 36 and 49 do not add up to make 121. So I know that that line right there is not a tangent, because it would have to make it, then that would be perpendicular, and we would have a true statement for Pythagorean theorem. So this is a whopping no, okay? All right, for the notes, we're not doing constructions this year at this point, so you can kind of skip this part, you know, of your notes. Let's go to the next page to finish up with tangents. Two tangents drawn from the same external point are always going to be congruent or equal, okay? Congruent or equal. So we've got a drawing here off to the right real quickly, this one at the top here. Let's kind of talk about that. So what we can do is, obviously I can make two triangles, right? If I go straight down here, like so, if these are tangent lines, then I have a 90-degree angle there, I have a 90-degree angle there. I have a radius here and a radius here. And remember, radiuses are congruent in the same circle. So I put a tick mark and a tick mark. And this line is shared by both triangles, so I can put two tick marks, let's say there, to say that, all right, what do we have? I have a right triangle and a right triangle that has two sides congruent to two sides and an angle, but it's not side, angle, side. These are not congruent by side, angle, side. These happen to be congruent because of, if this is a 90-degree angle, this is the hypotenuse. 90-degree angle, that's the hypotenuse and a leg. So these are congruent because of HL back in Unit 2 when we were dealing with triangles. All right, so I then know that these two tangents, once I know that these two triangles are congruent, these two tangents have to then be congruent because of CPCTC. Corresponding parts of congruent triangles are congruent. So I'm just now informally proving to you that this tangent and this tangent, when they come from the same external point going to the same circle, tangents will always be congruent that are drawn from the same external point to the same circle. Okay? And so here's two examples to show you that and to prove that to you. All right? Solve for x. So notice we have an external point. This tangent line, apparently, it's not going inside the circle. It's apparently touching the circle right there. And this line is touching the circle at this, like right there. They come from the same external point. 4x minus 7 should then be put equal to 3x plus 8. And I do that right here. Okay? And then I proceed to get my x's on one side. So I move this 3x by subtraction. I move this 7 away from the x side by adding it over here. And so x, 4x minus 3x is x. 8 plus 7 is 15. So apparently x is equal to 15. Now, we can then prove that. If you were to put a 15 there and a 15 here, do those measurements make the same? 4 times 15 is 60. 60 minus 7 is 53. All right? So that length there is 53 long. 3 times 15 is 45, plus 8, guess what? 53 long. So see, I just proved that two tangents from the same external point are congruent to each other. All right? And the last one, and then you're free to finish your homework for the rest of the packet. All right, so here I've got a tangent line drawn. Notice it's not going inside the circle, and it keeps going. You know, there's arrows at the ends here. So the issue is when they give you a measurement, that's not for the whole line, because the whole line just keeps going and going and going forever, but it's for wherever it's like touching that circle at that one spot. Okay, like right there is 77 long, and right here is 3x squared plus 2, just from there to there. So these two tangents are from the same external point, so they should be congruent to each other. So if I take 3x squared plus 2 and put that equal to 77, and now solve, subtract 2, 3x squared equals 75, divide by 3, x squared equals 25, square root both sides, x equals a plus minus 5. But because we're talking about specific lengths of something, your length of something will never be a negative value. So the only correct answer here is a positive 5, even though when we solved it, we got the plus minus symbol. In this situation, the only answer for x is 5. Now let's see if that's true. If I put a 5 right here, 5 squared is 25, times 3 is 75, plus 2 is 77. Boom. What did I do? I used PEMDAS to figure that out. All right? There were no parentheses. Then I did the exponent, 5 squared, 25. Then I did multiplying or dividing, so 25 times 3 is 75, and then I did adding or subtracting, plus 2 to equal 77, okay? All right, that is the end of this packet. That's day 1 and day 2, all right? Hopefully you've already done the bottom of this page. Hopefully you did this yesterday, and you've got all of that homework done. You should then finish the rest of the homework, which is the back side. Okay? Finish the rest of that, and you will be good. It's good to be back in our class, and I will then, if you're sick or quarantined, I hope this helps, and hope you get well, and look forward to seeing you again. All right. Peace out.